All right, so let's take a closer look at reality versus models. So let's say again we have this example of what reality is. We don't have any idea about it. Let's just assume it looks like this. And we have a certain assumption as to the class of models. So again, we don't have knowledge about x2, we only have knowledge about x1, and we assume it has a linear relationship with the response y. Now the point is, there's many different models in this class, potentially even an infinite number of models in the class. So how do we choose one? How do we make sure that that one is somehow the best we can make? All right, so let's talk about how we estimate the model. The thing is, we have some training data, some tuples, normally let's say we have n of them, of the form y, x. So we have a first observation and we have the y1, the response for the first observation, and we have the predictors for the first observation, x1. And of course, x can be multivariate, so we can have multiple predictors. Let's just say x1 for the set of features. And then we have a y2 given predictors x2 all the way up to observation n, which is the dependent variable n given the independent variables n. So n observations. By the way, these are also called instances or examples. So essentially the rows in our table. We have the table, n observations, we have the y, and then x1 all the way to xp. So assuming a certain class of models, again, capital F, we estimate the f hat that fits the data in the best possible way. This process of fitting to the data is also known as training, learning, or adjusting the model to the data. And then what best means, well, depends on what we're building the model for, what our problem is, what kind of models it is. It depends on the purpose of fitting the f hat. So even though the process is, yes, data-driven because we have a set of observations, the training set, domain knowledge may be leveraged, for example, through the choice of the class of models. So we may leverage our domain knowledge to say what class of models it is. Is a linear relationship with x1? Is it a quadratic relationship as we saw? Should we include this second variable x2 because we have domain knowledge and we know for sure that that variable affects the response? So the class of models, what predictors we use, again, we have to think about all the previous lectures to try and determine what is the best data we can have to build a model. And this will help minimizing the irreducible error, that part that is always going to be in there if we don't have a good study design, if we don't look at all the variables we should or in the manner we should, or if we make wrong assumptions about what the model should be. And now once we have a class of models, we may think about, okay, how do we actually come up with this function f? A very simple model would be what we call the nearest neighbors. And essentially the idea is that whenever we have a new observation, a certain value of the predictors of the x's, we just take all observations that are in the neighborhood of x. We're going to see exactly what this means. So all the data points that look like x in the training set. And then what we do is, well, just compute the expected value of the response for those data points, for the neighborhood. So our estimate, given some x, is going to be the expected response in the neighborhood of x, given our training set. So let's see. Let's say that we are modeling the relationship between y and x. These are our observations. Now, if we have a new data point, let's say x equals 6 over here, then how do we make a prediction? Or how do we say what the expected value of y is? Then we take a look at the neighborhood. Let's say this is the neighborhood of the point here of x equals 6. So those are the black points. And then what we do is compute the average response in those black points. That would correspond to this point here. So our estimate for x equals 6 equals 20. It's y equal 20. And if we do that all along the x-axis, we have a picture like this, which would be the model. So depending on which point along the x-axis we have, which specific realization of x we have, then we make a prediction for y just by looking at the neighborhood of x. Now the thing is, this idea, although very appealing and very simple, actually doesn't work very well for complex models. Um, it can work very well with simple problems if we have very large training sets, but when we have a large number of features, when P is large, we have many independent variables, it doesn't really work very well because it rarely covers the whole P dimensional space of all P features. The nearest neighbors, in reality, tend to be far away in high dimensional spaces. When we have a very large dimensionality, it's very, 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 very rare that we cover the whole space. So it could very well be the case that we have one observation in a certain point in the space, and then the closest neighbor to it is actually very far away in all P dimensions. And so we need some model that incorporates somehow structure in a more functional form. Something that is not just about looking at the data set, at the training set, and compute some kind of aggregate of the neighborhood. It's something that incorporates structure into the relationship between the X and the Y. And so when we try and find that structure, we typically talk about parametric or non-parametric models or learning methods. A parametric model is one that has a fixed set of parameters. So think, for example, a relationship between Y and X1 in this way. Then it has two parameters, beta 0 and beta 1. Always two, regardless of what data we have, the model is always about those two parameters. And so fitting the model is all about finding the best possible values for those coefficients, those parameters, given the training data. Finding good estimates of beta 0 and beta 1 such that they're optimal in some way. And then a parametric model is one that has very, very, very few assumptions about the data or about the structure of the relationship. And actually, in a way, the training examples, the training data are themselves the parameters of the model. So if you think about the nearest neighbors example that we saw earlier, the parameters of the model are actually the training observations, because ultimately the final observation for a new data point is going to be one that just aggregates a certain neighborhood, just looks at the very observations and just gives an answer based on the average. The parameters of the model are actually the training set, all the observations we have in the data. And so you see the difference is quite strong between parametric and non-parametric. The non-parametric models are expected to accommodate better to the data, but we're going to see they might suffer some problems. Parametric models are going to be worse normally into accommodating the data, into modeling the relationship, but they're going to be a lot simpler and a lot easier to understand. So let's see an example. Let's say over here we have the relationship between years of education, seniority, and how they affect the income of employees. And over here in blue we have reality. So this is reality, how it looks like. Let's say we have observations in red over here. For example, we have a person with a kind of high years of education, low seniority, and still here's the income coming from the model, from the blue one, from the process. Okay, let's say we have these observations. We want to build a simple model about it. And we could choose a parametric model, something like here in yellow. It's just a plane in this three-dimensional space. Well, it's simple. Might not be flexible enough to accommodate certain observations, like maybe this one over here or that one over there, but still it looks like it's a reasonable model of what reality looks like, right? So it's going to be useful for us probably to understand the relationship between the variables in this case. So it's a simple model. It's something that is very well studied. It's easy to interpret, just perhaps not flexible enough. If we want to look for more flexibility, then we can think about a non-parametric model. So it could be something like the one we have here. And we see it has these warps, these bumps in the space to try and better accommodate these nuances in the data. And yeah, it looks like it's a better model. It's just more complex to reason about it because now the relationship between years and education and income is not just this straight line, but perhaps it's just what we're looking for, just the right amount of complexity. It depends on what we want to do with the model. And so at some point, when we're thinking about the complexity of the model, how simple it is and how well it accommodates the data, we have to think about the phenomenon called overfitting. So in general, the point is we can always or near always obtain better fits to the training data just by allowing more flexibility in the model, by allowing the model to be more complex, to warp in a stronger way. This often translates into adding more parameters. So if we keep adding more and more coefficients to the model based on the relationship between the variables and the response, then we're going to allow the model to vary in more, for example, non-linear ways to try and accommodate all the training observations. But at some point, the model is going to be too complex. So complex that it's really not a good model of reality. It's just a good model of our training data. At some point, it might even be a model that perfectly fits the training data. It goes right through all the observations in the training data, but then it gives very poor estimates on new data because it's just a very bad model of reality. It's a perfect model of our data, but not of the reality that the data comes from. And so it kind of remembers the instances in the training set when we want to make predictions, for example. It doesn't learn well the underlying patterns in the data, the underlying reality. It just kind of learns where the observations are, and that's it. Predictions on new unseen data are going to be very poor. If the model is too complex, then it's going to be too difficult to interpret, and it's not going to help us understand the underlying reality, which again in our course is what we are after. And so it's just about finding the right balance between how complex the model is and how useful is it to understand our reality. If we go too complex, then we have a very good fit to the training data, but it's a model that really does not model reality. And if we have a model that is too simple, it might be, well, too simple to really capture the complex nature of reality. It's about finding the right spot. And so, for example, if we go back to the case of income as a function of years of education and seniority, we might find this model over here in yellow that warps a little bit more than we had earlier. And it just so happens that it goes right through all the observations in the training data. So the model fits the data even better than reality itself. This model in yellow fits the data even better than the process that generates the data. This is a model that is overfitted. It's only a model for the data. It's not useful in any way because, well, we don't want a model for the sample data. We want a model for reality. And so we have to find this balance between the complexity and how well the model describes the reality, how useful it is for us to understand reality.